Hello and welcome to the course Introduction to Brain and Behavior. I am Dr. R. Verma from IIT Kanpur. This is the seventh week of the course and we're going to talk about neural models of language. Now, several neural models of language comprehension have been proposed so far. In the contemporary models, however, that these classical language areas are no longer always considered language specific, nor are their roles in language processing limited to those proposed in the earlier classical models. An example of a classical model would be Ludwig-Lichtheim's model of language processing, which you may remember that there was a Broca's area, there's a Vernix area, and there's a conceptual area. Basically, all three of them are connected, and if different and the pattern of connectivity between these areas are ruptured, then different profiles of aphasia emerge. So, but the difference is that in more contemporary models, as the understanding of neuroscientists have increased, people are sort of the opinion that whatever areas have been included in the neural network of areas that understand and produce language, basically what happens is that none of these areas are exclusively dedicated to linguistic processing, or for that matter, none of these areas are doing only language processing. They are probably doing involved in other parts, other activities as well. Further, additional areas have also been added, have also been implicated as part of the circuitry that is used for normal language processing. Now, in a more recent neural model that was proposed by Hegut and colleagues in 2005, language processing can be divided into three kinds of functional components: memory, integration, and control. Let us look at them in some more detail. Now, memory or area or the aspect of memory basically involves storage of information in the mental lexicon and retrieval of information from the mental lexicon. Basically, the long term, basically the lexicon acts as like a long term memory store for word information. Unification. Unification basically involves the integration of lexically retrieved phonological, semantic, and syntactic information into an overall representation of whole utterances. In language comprehension, the unification process for phonological, semantic, and syntactic information can operate in parallel with each other, and the interaction between these different types of information is also plausible. Integration makes Hagut's model a constraint based interactive model. Now, control basically deals with the aspect when linguistic processing is combined with an action. See, for example, if you are a bilingual, you have to choose between two kinds of language acts. Language act of producing language in your first language versus an act of producing language in your second language, basically, and also switching between the two languages as and when the need arises. So all three of these processes together are seen to form whatever the entire language network is supposed to do, and there will be areas of the brain that will be performing these different tasks in a sort of an interconnected manner. Let's see this in some detail. Now, as per this model, the temporal lobes are implicated as being important for storage and retrieval for mental representation of words, mental representation of words. The phonological and phonetic properties of words are supposed to be stored in the central to posterior superior temporal gyrus, extending up to the superior temporal sulcus, and the semantic information is supposed to be distributed over different parts of the left, middle, and inferior frontal gyri. Inferior temporal gyri, sorry. Now, the processes that are involved in integration of phonological, lexical, semantic, and syntactic information are supposed to engage the frontal areas of the brain, including the Broca's area or the left inferior frontal gyrus. This left inferior frontal gyrus also seems to be involved in three kinds of integrative processes. First is semantic unification in the Broadman's area 47 and 45, syntactic unification in areas 45 and 44, and phonological and phonological unification in Broadman's area 44 and 46. The control component of Fagut's model basically comes into play when people are actually involved in communication. For example, when they have to take turns during a conversation, there is where the control part also comes into place. Now, the concept of cognitive control in language comprehension has not been studied in much detail, although the areas that seem to be engaged are also thought to be involved in cognitive control during other tasks. Say, for example, the same areas of the brain that are involved in dual task scenarios might also be involved in in situations where two languages have to be used interchangeably. They are the anterior cingulate cortex and the dorsolateral prefrontal cortex. So these are the areas that are probably assigned the task of control. Now let us look at the network of the left hemisphere language system in a bit more detail. Which you can ask which areas of the left hemisphere form a network that is involved in language functions. Now recent studies have shown that have investigated the functional and structural connectivity in the language network have identified several pathways that connect the representation of words in the temporal lobes to the unification areas in the frontal lobes. Say, for example, for spoken comprehension, Federici has elaborated a model of language network that includes the connecting pathways. According to this model, there are four kinds of pathways. There are two ventral pathways which connect the posterior part of the temporal lobes with the anterior temporal lobe and the frontal operculum. These ventral pathways are important for comprehension of word meanings. The two dorsal pathways connect the posterior temporal lobes to the frontal lobes, and the dorsal of the two, and between them, the dorsal of the two connects directly to the premotor cortex and is involved in speech preparation. The other connects the Broca's area with the superior temporal gyrus and superior temporal sulcus and is involved for aspects of syntactic processing. Let's talk a little bit about neural models of speech production. Now, one of the more influential models of speech production was put forward by William Levitt in 1989. According to this model, the first step in speech production is conceptual preparation. Okay, Levitt proposes that there are two crucial aspects of conceptual preparation. One is macro planning and the other is micro planning. At the level of macro planning, the speaker needs to determine the content of the message. What do I want to say? Suppose I have to, present a weather report. What do I know about the weather? What is the weather now, and so on. Nowadays a lot of people are making video blogs, and one of the things that they need to decide probably before starting a blog is to think about what broadly do they want to talk about in their video blog. Okay, at here the intention of the communication as represented by goals and sub goals is becomes part of this overall communicative plan. So that is the macro level. And on the other hand, at the micro planning level, basically one needs to formulate how the message is to be expressed, adopting a particular kind of a perspective to convey the information. Okay, so you're suppose you want to present the weather as nice, or you're just not not liking the weather and you want to criticize the aspects of the weather. The microplan would determine the word choice, which words will you use, and the grammatical role and how will you use them. Past tense, present tense, continuous tense, how. So this is here you can say William Levitt's model. So it starts at the level of conceptual preparation in terms of lexical concepts. The idea is basically lexical concepts are concepts for which your language has a word. So for example, if you want to talk about a female elephant, English does not really have a specific word for female elephant. So it will basically use female and elephant, but it has a word for a female horse. So there it will use the word horse. It will use the word mare. So mare is the word that depicts a female horse. So basically the conceptual preparation will happen. It will align all the lexical concepts. Basically whatever I wanted to say, and do I have the words for it or not. And these words are lexical concepts. Because several lexical concepts can be activated simultaneously, there is a need for something called lexical selection. Once you have selected the correct word, then you go to what is called a lemma level. And a lemma level is where, again, it's a hypothetical level which basically contains information about the syntactical and semantic aspects of the selected word. Okay, once you have the lemma level, say for example you have decided that I'm going to talk about the word eat and I'm going to talk about it in continuous sense, then eating is the word that needs to be selected. Going further, what will happen is morphological encoding will happen, and morphological encoding is nothing, it's basically activating the morphemes of the language. So I want to talk about the word concept eat, I want to talk about it in continuous sense, so the word that suits it is eating. Eating is composed of two morphemes. One is eat, which is a free morpheme, a lexical morpheme, and the other is ing, which is basically a bound grammatical morpheme that has to function with the word eat. So this is called morphological encoding. From here you kind of come to the identification of the two separate morphemes. Once you have identified the morphemes, then basically what you will do is you will engage with phonological encoding, basically activating the sounds that will compose those morphemes. Once you've activated the sound, say for example eat, then basically you will have to syllabify them. You'll have to arrange them in articulatable chunks, which are which are basically in forms of syllables. So eating basically has two syllables, e and ting. Okay, so even though the morphological composition is eat plus ing, the syllabic composition is e and ting. Okay, so you kind of have to become aware of that. Once you have activated the syllables and you've organized them nicely, what forms or what comes out is the phonological word, which is basically what you hear. So here you can see from the aspect of phonological word, you can see that there is this self-monitoring, because from here itself you can hear almost yourself speak the word. Once the phonological word is prepared, then you can move on to phonetic encoding, which is basically moving your articulators, etc., preparing them that okay, this is how this is what has to be produced, and the programs for articulating each of these words have to be put in order. That is basically what is a phonetic gestural score, which is a program for executing the word. Finally, you do the articulation, you create the sound wave, which again you can hear. So this is just a brief description of Level's model of speech production. So let's just go and visit it in some detail. Now the outputs of the macro planning and the micro planning stages is a conceptual message that constitutes the input for a hypothetical formulator, which is a mechanism that puts the message in a grammatically and phonologically correct form. During the grammatical encoding, a message's surface structure is computed. This surface structure is basically the message or the gist of this, syntactic representation, including information like X is a subject of or Y is an object of, and that needs to be very well specified by the use of the grammatical word order and so on. The lowest level elements of this surface structure, that is the lemmas, which are these words, are about a word's syntactic properties and its semantic specifications. And also the conceptual conditions like where and how the word has to be used. I was talking about the word eating. Where do you want to use the word? Eating is doing something, so you cannot start with the word eating. So John likes eating. Maybe that makes more sense. So all of these details need to be really worked out. Now these types of information in the mental lexicon are organized in a network that link lemmas by meaning. So what each of these lemmas mean, how are they used, etc., can be organized in the mental lexicon itself. As per the Levitt models, as you've seen, there are a series of steps that proceed when someone is presented with the picture and asked to name. As the first step, the concept that I've already explained to you while the picture was there, but I'm just kind of going through this again. As the first step, the concept that represents the picture is activated along with other semantically related concepts. Activated concepts in turn activate representations in the mental lexicon, starting with nodes at the level of the lemma to access the syntactic information such as word category. Moving further, lexical selection needs to happen and the syntactical properties of the word that represents the picture need to be retrieved. So, what is the picture that you're seeing? If you're seeing a picture of a verb, let us say somebody is cutting something, then you have to remember that, okay, the syntactic information is that this is a verb, it is a continuous form of the word, and so on. The word form then goes through a stage called morphological encoding, whereas the components of the word's exact word, the morphemes, need to get activated. The newly activated morphemes contain both phonological and metrical information, basically how they are going to be said. Then, broadly, you're going through the process of phonological encoding, which maps the phonological information to the metrical information, just like syllabification. Going further, the appropriate word form is selected and the phonetic and articulated programs are matched, and then you're ready to produce. In the final phase, the word syllables are mapped onto motor patterns, how the articulation will be done, and that move the tongue, mouth, and vocal apparatus to the to generate the word. At this stage, individuals can repair any errors in the speech by saying, maybe I'm saying this incorrectly, let me correct this and re-utter this word. Okay, so this sort of allows them to regenerate the appropriate term. Now, brain damage can actually affect each of these processing stages. For instance, some patients who suffer with a disease called anomia have deficits in naming objects. They're able to give accurate descriptions of the object in the presented picture, but would not be able to name the word. It becomes clear that the problem is not with the articulation, but at the word level. Similarly, patients with Wernicke's aphasia produce semantic paraphasias, as we've talked earlier, wherein they are capable of producing words related in meaning with the target word but not the target word. These patients also make errors at the phoneme level by incorrectly substituting one sound for another. Finally, Broca's aphasia patients are often accompanied by problems like dysarthria, where it creates problems in articulation and results in effortful speech, because the muscles that articulate the utterance cannot really be properly controlled. Now, contrary to the approach espoused in Level's model, Gary Dell put forward the interactive activation model of speech production. According to Dell's model, phonological activation starts shortly after the semantic and syntactic information of words has been activated. Dell's model allows for feedback and cascaded processing, and hence, what happens in this model is that feedback flows from the phonological activation to the semantic properties of the word, thereby enhancing the activation of the certain target words. Sahin and colleagues in 2009 recorded electrical responses from several electrodes implanted in and around the Broca's area during pre-surgical screening of 3 epilepsy patients. To investigate word production in the brain, these patients were asked to do a task which involved 3 conditions that would differentiate lexical, grammatical, and phonological linguistic processes. It seemed that the brain waves were correlated with different stages of the speech production cycle. At the first wave occurred at around 200 milliseconds. It appears to index lexical identification. Another wave came up at 320 milliseconds and was modulated by inflectional demands, and the third wave at around 450 milliseconds, basically reflecting phonological encoding. So basically what you can see here is that as per Level's stages of memory, this probably is happening in serial. So at 200 milliseconds lexical identification, then inflectional demands, lemma level at 320, 450 milliseconds you can see phonological encoding taking place. Another wave happens at around 600 milliseconds, which basically indexes the activity of motor neurons. So now you are already in the articulation phase. So in all, basically you can see that these findings actually provide support for serial processing during speech production. So the evidence probably lies more in favor of Level's model. Now, for instance, inflection processing is not occurring, till the word was identified. So it's not preceding the lexical identification phase, but is happening after it. And phonological processing is not occurring until the inflected phonemes were selected. So you can see that there is a degree of serial processing involved here. Now, these results were found to be consistent with the idea that the Broca's area has distinct circuits that process lexical, grammatical, and phonological information. Neuroimaging studies of the brain during picture naming and word generation tasks have shown that activation in the inferior temporal regions of the left hemisphere and in the left frontal operculum. So basically picture naming involves these areas. It has been proposed that the activity in the frontal operculum can be linked with phonological encoding in speech production. The articulation of words probably involves the posterior parts of the Broca's area, but also some studies have shown bilateral activation of the motor cortex, the supplementary motor area, and the insula. Further, PET and fMRI studies of motor aspects of speech have shown that they involve the supplementary motor area, the opercular parts of the precentral gyrus, the posterior parts of the inferior frontal gyrus, the insula, the mouth region of the primary sensory motor area, the basal ganglia, and the cerebellum. So you can see that the entire gamut of areas that are involved in motor processing in general are also involved in speech production. It is therefore established, if you look at this in a holistic sense, that is a widespread network of brain regions, predominantly located in the left hemisphere, is basically what is involved in most people for production of speech. This is the last lecture of 7th week. I hope that you have understood neural aspects of language processing in this week, and I'll meet you next week with another chapter. Thank you.